Welcome back to the C programming language in action. Although this module is mostly about structures, we're also going to look at unions and enumerations, which are closely related. Structures are used to build more interesting types, more expressive applications, and in particular, more interesting libraries. Unions and enumerations can help to a lesser degree. Let's take a look. In this segment, we're going to look specifically at structures, structures being a collection or sequence of variables. Those variables may be of any type, so this is unlike the concept of an array. Consider a simple point, perhaps, in a graphical application that uses floating point values for its logical coordinate system. Something like this. And then, perhaps it requires a way to represent colors using RGB, red, green, and blue values. These might be represented using integers, perhaps only requiring a single byte per color channel. With 8-bit bytes, we should be able to provide a range of values from 0 through 255 for each color channel, sufficient for some simple graphics. This will quickly become unmanageable as the application grows and requires more data or state to be represented. These are trivial bits of information, but the concept is the same regardless of whether you want to create a user-defined type for a pixel or for a TCP network packet. So we might start by defining a type for pixels. How about the color? Well, I hate typing unsigned char, so let's use the typediff again. Now I can add another structure to define a color. With these type definitions, I can replace the assortment of variables in my main function with something a little more expressive. First, the pixel coordinates. And then the color values with a single variable. So these declarations inside my main function are just straightforward variable declarations, just like what we saw in the previous module with its fundamental types, except that now we're using types that we've defined ourselves. There's just one little problem. Although this code works perfectly well with any C++ compiler, the C programming language inexplicably places the names of structs in a separate namespace, so they're not actually directly accessible in this manner. The C way to deal with this is to explicitly tell the compiler to look up these names in the struct namespace. I don't know about you, but I find this rather tedious. One option is to use typediffs to introduce the structures. Alternatively, you can wrap the pixel structure definition within a typediff. It makes no difference to the compiler, but a lot of people prefer it. Given this definition, you can also omit the name of the structure and simplify this even further. The only reason you might not want to do this is if there were a function with the same name as the structure. So if there were a function called pixel, the compiler would complain that these names in fact conflict. I would simply avoid giving a function the same name as a structure and vice versa. Anyway, I can now remove the struct prefix from the main function's pixel variable. Obviously, I can do the exact same thing for the color structure and variable. This approach of using a typediff to wrap a function is handy because it works equally well with C++ compilers, So if you're working on a library for both C and C++ developers, this is a way to give both a simple and consistent programming experience using your library. Now, of course, being a variable declaration, we should expect to see the type, here pixel or color, the variable name, here P and C respectively, but what about the initializer? Well, fortunately, you can also initialize variables of structures. It just takes a bit more syntactic sugar to make it happen. In this case, the pixel's X member will be initialized to 10 and the Y member to 20. The so-called curly braces are used to write an initializer list, a list of values with which to initialize the variables of these structured types. Remember, structures are sequences of elements or variables, so we can initialize these variables with sequences of values. Any trailing members for which values are not provided are simply zero initialized. In this case, red is 255, green is 128, and blue is 0, giving an orangey color. Once initialized, the variable members may be accessed with a member or element selection operator, the period or full stop character. I could return the x-coordinate as follows. And I can simply use assignment to update a member directly. Now we've got a nice pink color. Segment, we're going to take a look at the ways in which structures are laid out in memory, how this might be controlled, and what it means to pack a structure. This might all sound rather low level, but C is often used for such tasks where memory layout is essential. Even if that's not the case for your purposes, having an idea of how your structures fit into memory can help to diagnose strange problems and improve the performance or efficiency of your applications. Consider a simple structure with a mix of data types. We'll mix some shorts and some ints. Recall that short is just an abbreviation for short int, while int is a regular integer. So it's likely on most platforms that short will occupy less space than int. But let's confirm. Let's print out the sizes so we can be sure. And then the int. And then, just for fun, the structure as a whole. Okay, let's see what happens. So it's compiled. Let's run it and see what it reports. So that's interesting. We can see that this compiler reserves 2 bytes for a short, so shorts are 16 bits wide, and ints occupy 4 bytes, or 32 bits. No real surprises there. But the structure as a whole occupies 12 bytes. That seems a little strange. We know that the structure contains 2 shorts and a single int. 2 shorts make up 4 bytes, plus the int, which is another 4 bytes. We should have a total of 8 bytes, not 12. What gives? Well, there are 2 factors at play. C and C++ requires that the members of a structure are laid out or allocated in declaration order. So the address in memory where first is found must be less than second, whose address must be less than third. The second issue is that most processors today either require or strongly prefer that types are aligned properly in memory such that they begin on an address boundary that is some multiple of its size. So if the second member, the integer, were placed immediately following the first, it would be misaligned. What ends up happening is somewhat platform and compiler specific, but it's also quite common to have the same layout, at least on the same machine, since it's the machine architecture that defines the layout requirements. In this case, what we're seeing is some padding introduced to ensure that the second member falls on a 4-byte boundary relative to the start of the structure. Something like this. So the first short occupies 2 bytes, followed by 2 bytes of padding. And the second now comfortably occupies the next 4 bytes and is properly aligned thanks to the preceding padding. And finally, the last short also receives 2 bytes of padding. You might be wondering why those last 2 are required. After all, there are no remaining members that need to be aligned. Well, the reason for that is to ensure that multiple structures, perhaps in an array, are all properly aligned. Of course, if we reorder the members, then the compiler is once again free to optimize the padding as best it can. Let's move the third element before the second. Now the padding disappears. Since the 2 shorts are properly aligned and their storage combined ensures that the integer is also properly aligned, no further padding is required. But let's check. And let's see what this reports. And sure enough, the structure now occupies just 8 bytes, 4 bytes for the 2 16-bit shorts, and another 4 for the 32-bit integer. In this segment, I'm going to show you how to work with unions. I only show you this about unions because you're likely to come across it, not because it's a particularly good idea. I've come across only a handful of legitimately good reasons, mostly to do with awkward APIs that need to be dealt with. Still, the idea is simple, so let's take a look. In the next segment, we'll look at something very similar called enumerations. The C construct of an enumeration is problematic. C++ 11 introduced a much stronger notion of an enumeration, which makes C-style enums look truly ridiculous. Still, for starters, let's look at unions, and then we'll look at enumerations. A union is much like a structure, except that all of its members share the same address. So I can add one member, just like in a struct, and another. Now this looks very much like a struct. But remember, when I introduced structs, I mentioned that the elements are laid out or allocated in declaration order. If this were a struct, the address of real number would be greater than the address of integer. But in this case, since it's a union, they both share the same address, and the size of the union as a whole is as big as its largest member. On my machine, int and float are both 4 bytes, so this struct, or union I should say, is also 4 bytes long. But let's check. So that's the size of an int, and then the size of a float. And the size of the aggregate. Oh, remember that in C, names of unions, like structs, live in their own namespace. So we need to either do this, Or use the typedef trick again. Okay, let's see what this produces. No complaints. And as expected, int and float are both 4 bytes on my machine, and the union itself is also 4 bytes, the least amount of space required to hold any one of the union's members. If we had to switch this up in changing the float to a character and print out the size of the character, recompile, and run, and again we can see that despite that characters only occupy 1 byte, the size of the union remains unchanged, since it must accommodate the 4-byte integer. But if we change this union into a regular structure, and simply recompile and run, immediately the size of the aggregate jumps to 8, since the integer and character no longer share the same starting address, and the alignment is such that the structure includes some padding at the end. And that's unions in a nutshell. They are sometimes useful for converting between union members, but this is very risky and should be avoided unless you know exactly what you're doing. In particular, if the members are not the same size, you're not going to get sensible conversions. One of the challenges with unions, such as this, is that the compiler or runtime has no way of knowing what type is actually stored in the union, or what was last written to the union. Inevitably, you need to store some extra information to indicate the type. One way of doing that is with an enumeration. An enumeration is some type that may hold one of a given set of values, integer values or constants. We might create an enum to describe which one of the values in this union is the one presently holding a meaningful value. Now we can declare a variable of the union type and assign it a value. We can then declare a variable of the enum type. But as with structs and unions, the name of the enum lives in a separate namespace. Again, this weirdness with the names of structs, unions, and enums is only present in C. C++ does not suffer from this, but this code is then portable across both C and C++. So now in our main function, we have our union with its integer value and the enum telling us as much. We can now give the union variable a new value of a different type. And update the enum accordingly. Finally, I should point out that the enum's members, called enumerators, are simply integer values. You may initialize them with whatever value suits you. Otherwise, the compiler will assign them values beginning with a 0. Let's see. And after changing the type, okay, let's give it a try. So here we can see the union's value is initially 123, and its type is 0, which corresponds to the first enum value, the integer. Then the value changes and is v as expected. The type is 1, the second enum value. We can go ahead and change the values in the enum if we'd like. Everything works as before, but the actual values for the enumerators have changed. So you can use values that make sense for your application. In this module, we've explored the essential ingredients in building more interesting aggregate types by combining various fundamental types into structures. While structures are quite simple, they do suffer from an odd quirk in C in that the struct names are declared in a separate namespace and must be declared explicitly as structs. You can, however, use a typedef, as I illustrated, to make C structs behave more like C++ structs. We explored the essentials of layout for different machine architectures and the inevitable padding that follows to ensure that types are properly aligned. This alignment is only needed if you wish to address the members, and more interesting but dangerous solutions such as packing and bitfields may be employed if necessary. We also looked at unions, a somewhat tricky structure which allocates its members at the same base address. And enumerations, often called enums, which provide a set of enumerators. Enums are useful, but C++ adds enum classes, which are much more intuitive, reliable, and convenient.